right. Okay. This Zoom session is being brought to you by the fractal horizon forming. All right. For today, we start chapter 2. This is about angles and their measures. All right. An angle. It looks like this. It's two half lines with a common vertex. This is the vertex. It's considered to have an orientation, rotating from the initial side to a terminal side. If it's counterclockwise like this, it's considered a positive angle. If it's clockwise in the opposite direction, that's considered a negative angle. Okay. Now, what kind of, you can measure an angle, and what kind of angle depends on its measure. If its measure is less than a right angle, like this, less than 90 degrees, this is called an acute angle on account of the sharpness of the point here. This with a square corner here, it's called a right angle. Here, if it's beyond 90 degrees, but less than 180 degrees, it's called an obtuse angle. Here, 180 degree, it's actually not considered, well, it's usually not considered an angle at all, but, or it's called a straight angle, 180 degrees. Now here we get beyond, here we start getting beyond. Here, if it's beyond 180, but less than 270 degrees, this doesn't actually have a name. I call it a breakback angle. Here, if it's more than 270, but less than 360, again, it doesn't have a name. I call it a Pac-Man angle, thus dating myself. Can you still play Pac-Man? Is it still out there? Oh, never mind. Here, one full rotation is known as, it's 360 degrees. And of course, you can go beyond. You can rotate several times around. All right. We usually put the angle in what's called a standard position, where the initial side is the positive x-axis and it rotates to the terminal side. Here it's 0 degrees, 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, up to 180, from there up to 250, 270, excuse me, from there back to 360 degrees, which is the same as 0 degrees. One rotation is 360 degrees. Now we can divide up degrees. It's tradition to divide up degrees into 60 minutes, denoted by a dash. So 1 degree is 60 minutes. And we divide up 1 minute into 60 seconds, 60 double dash. And yes, these minutes and seconds are in fact related to the minutes and seconds that you experience in a clock. This whole method, this whole notation, the degree minute seconds notation, called DMS, it's really old. It goes back to Babylon. Oh my God. Really, I mean, that's how traditionalist math can be. And of course, it was used by, we know this because it was notated on various archaeological digs where they were doing, guess what, astrology. So anyhow, so D degrees, M minutes, and S seconds. Well, it's D plus M over 60 degrees plus S over 3,600 degrees. So there we go. So for example, 40 degrees, 10 minutes, 25 seconds is how many degrees? Well, it's 40 plus 10 60ths plus 25 over 3,600. And after a bit of arithmetic, that's 40.1736111111 degrees. 9 degrees, 9 minutes, 9 seconds, 9 degrees plus 9/60th of a degree plus 9 over 3,600th of a degree gives you 9.1525 degrees. Now I can go the other way around. 40.32 degrees. This is decimal degrees. It's how much in degrees, minutes, seconds. So it's 40 degrees plus 0.32 degrees. All right, now you take this 0.32 degrees and multiply by 60 to get how many minutes, namely 19.2 minutes. Okay, so we have 40 degrees, 19 minutes plus 0.2 minutes. Multiply that minutes by 60 to get 12 seconds. 40 degrees, 19 minutes, 12 seconds. Or here, let's convert 18.255 degrees, decimal degrees, convert to DMS. Okay, here it's 18 degrees plus 0.255 degrees, multiply by 60, that's 15.3 minutes. So 18 degrees, 15 minutes plus 0.3 minutes, multiply by that by 60, and you get 18 degrees, 15 minutes, 18 seconds. Well, all right, it's really kind of charming to use a system of measurement that goes all the way back to the dawn of civilization. What can I say? That's amazing, I think. But It is kind of artificial. Why specifically 360 degrees? Well, it's kind of pretty highly divisible. You can divide it into halves and quarters and thirds and fourths and fifths and sixths, not in sevenths, but yes in eighths, not in nine, well, no, not in ninths, but yes in tenths, and so on. All right. So it's pretty highly divisible. And 360 degrees does happen to fairly close to the 365.25 days in a year. And since they're using this for astronomy / astrology, the implications were obvious. But still, in math, it's really better to not have to rely on something bound by tradition and culture, but rather have something that's inherent to the things themselves. It's a kind of respect for abstract objects. So I'd like to have, so in mathematics, we invented something called radian measure, where one rotation is considered to be 2 pi radians. And why 2 pi? Well, here's the idea. You take an angle, put the vertex at the center of a circle, then here's an angle, theta, we'll measure it in radians. The circle has a radius r. This has an arc length of s. And the radian measure is s divided by r. That's in some sense abstract, non-human cultural. It has to do with the circle itself. So it'd be talking to the circle on the circle's own terms. So since if you go one unit or one circumference around is 2 pi times r, then 360 degrees, one full rotation, is 2 pi radians. Okay, or reducing it a bit, pi radians is 180 degrees. So the ratio between these two, pi radians and 180 degrees, is 1. So we call that a unit conversion factor. Pi radians divided by 180 degrees is 1. 180 degrees divided by pi radians is 1. Therefore, you can multiply any angle measure by one of these to convert from degrees to radians, or to convert from radians to degrees. For example, 45 degrees, we multiply that by pi radians over 180 degrees, partly because this is 1, and radians per degree, so that degree measures will cancel out. And after a bit of arithmetic, that's pi over 4 radians. Conversely, 1/2 of a radian, 0.5 radians, we'll multiply that by 180 over pi degrees per radian. So the units of radians will cancel out, and we're left with 90 over pi degrees, which is approximately 28.65 degrees. Now, going back to our circle with a pi slice out of it, well, maybe not literally pi. Anyhow, angle theta in radians, remember, you have to measure in radians or this formula won't work. And radius r, and a is the area of this sector, then a is pi r squared theta, again, where theta is in radians. If you try degrees, you'll be wrong. So for example, if a circle has a radius 0.75 meters and an angle of 15 degrees, what's the arc length of the slice? What's the area of the slice? Well, first, again, we have to return this 15 degrees into radians for the formulas to work. So 15 degrees times 1. In this case, we make it radians per degree, so the degree measure will cancel out. 15 pi over 180, after some reduction, that's pi 12ths radians. So having gotten that, now we can use the formulas. S is r theta, therefore 0.75 times pi over 12 meters in meters. And so that's pi 16th meter, or 0.1963 meters to 1 part in 10,000. Area is pi r squared theta. So 1/2 r squared theta, my apologies. Okay, 1/2 times the square of 0.75 meters times pi over 12. Okay, so bit of arithmetic, 3 pi over 180, 28 square meters, or 0.07363 square meters. So more examples. 7/12 pi radians is what? Well, This is radian, so I want to multiply by degrees per radian. And it's 180 over pi degrees per radian. And then here, after canceling radians, times 7 pi over 12 and some arithmetic, you get 105 degrees. Question?
Teacher?
Yes, sir.
Earlier, when you said the 360 degrees are 2 pi radian.
Yes.
Why is that?
Well, again, let's go back to thank you for asking. Okay, so start with a circle, you see, and has a radius r, and let's go around 2 pi, a distance, arc length of 2 pi. Well, the circumference, the circular distance around a circle, is 2 times pi times r. So if you divide 2 pi r by r, you get 2 pi. And since one rotation is 360 degrees, that's why.
Okay.
Thank you. Thanks for asking. Negative 40 degrees. Now that's a clockwise rotation. How many radians? So, okay. Degrees here, so we have to multiply by radians per degree for the degrees to cancel out. So it's negative 40 degrees times pi radians for every 180 degrees. After canceling and reducing, that's approximately negative 0.69813 radians to 1 part in 100,000. All right. Here we have circular sector. The angle is 42 degrees. The radius is 17 centimeters. What's S? The arc length of the sector. What's A? The area of the sector. Okay. As before, we must convert 42 degrees to radians. So take 42 degrees and multiply it by radians per degree, so the degrees will cancel. And it's pi radians for every 180 degrees times 42 degrees. And after some arithmetic, it's 0.733038 radians. So use that in the formulas. S is r theta, r is 17. Theta is about 733.038. And so therefore approximately 12.5 centimeters. You'll notice I only do this to 1 decimal place accuracy. Even though this is, I did to 6 decimal places, but this was only known to no decimal places. So this is actually more than is really justified. Just one more though. Generally don't go much further in your accuracy of if you're giving approximate answers, don't give accuracies in terms greater than the accuracy of the input data. Here, A is pi r squared theta. Well, I get half r squared theta. I keep saying pi. My apologies. All right, so 1/2 times the square of 17 centimeters times 0.73038 approximately, and some arithmetic, 105.9 square centimeters. And again, I go to only 1 decimal place because that's only just barely more than enough the accuracy than the data itself justifies. Oh yes, about accuracy, the degrees of decimal degrees of accuracy. Like I say, it's just, if you're going to give an answer in problems, either give the exact answer with the square roots and the pies and so on, or if you're to give an approximate answer, give the approximation and at most 1, or really only more than only the accuracy of the data, or maybe 1 more just to be on the safe side. But don't go further. There's a story that illustrates this. The docent at the museum was guiding a group through the museum, and they stand in front of this enormous skeleton of a dinosaur. And the tour guide said, "This dinosaur lived 75 million years ago." The guy in the back of the crowd says, 75,000,001. You gave the same lecture last year. All right, never mind. All right, I think we're done for now. So where did I put this? Second. Stop. Stop video. Ooh. Sorry, that's not what I meant. stop recording.